Okay, so what have you got here? This would be, instead of adding c in the exponent here, maybe that looks a little bad handwriting, times e to the c here. This, yeah, absolutely. This is just a constant, and instead of writing it as e to the c, just write it as k or whatever you want, right? Something else. If you look at it, though, you're actually going to realize what it is, because so this is where I'm going to write it in front, because you usually write constants in front. It's actually equal to the initial population in this case, because if you were to put in, if you were to put in 0 here, what does this whole term equal? 1, right? It equals 1?
1, yes. Yes.
So, well, you could call it K or whatever you want here. You could call this thing, but it's the initial population, P0, because I mean you can see that just by putting in a 0 there. This whole term is 1, right? It's a 1, so it's not even there. So the population when you put in 0 is that, right? E to the C, whatever you want to call it, and it's the initial population. This matches up pretty closely with what you had from last year. If you write this down below, you had, well, we had 1,000, which was the initial population here, right? 1,000, 1.05 to the T. You have, last year you had P0 times 1.05 to the T. So we're going to compare those two things before we go any further along here. If you compare those two things, look at what's the same here. You have initial population, and you have, well, this, of course, over here is the same. You have this T is the same, right? So what's the difference there? Yeah, e to the 0.05 and 1.05 here. They are very close. Have a look at what they are in the calculator. They're very close to each other. If you go,
that's too big.
If you go e to the power of 0.05, you get approximately 1.05. The difference that comes up there is because of the fact that this model we're using now with base E, and it assumes the population is growing continuously. Like as soon as there's new people added, they contribute to the fact that it's getting bigger, the population, or whatever it happens to be. It's continuous growth. This we looked at where E came from early on in the year, the beginning of the year. If you look back at that, we did it with compound interest compounding more and more often. So this is like if it's compounded continuously, like the instant there's some new part, it's added to the amount. Okay, so you can look back on that and make that connection if you want. What about last year though, if you had things that were, if this was declining at a certain value? Like if this was going down at 5%, what would you have in here from last year? This would be 0.95. What do we have to go e to the power of? What would this be though? Like if we had started here and said it was going down at 5%. Yeah, this would have been negative 0.5. If you try doing e to the negative 0.05, it's approximately equal to 0.95 if you check that. E to the power of negative 0.05. Okay, it's approximately equal to that. So this exponential stuff, it does come out of that initial premise that your rate of change is the same, is related to the size of the population. If you wanted to actually write that here, which we never did, well, you put in the initial population, I guess, if we wanted it. It's 1,000 times e to the 0.05 t. For exponential growth, you can, of course, just write that right away because all the steps in solving are always going to be the same if you know this number off the bat. You might not know that number right off the bat. You might just know a couple points along the way. You used E a little bit in grade 12, but not a lot. if you have anything where y is changing at a rate proportional to the amount present, if the rate of change of y is proportional to the amount present, you can say y prime is k times whatever that value is, right? And it's going to, if you solve it all the way down here, you're going to get y is equal to whatever the initial population or initial value is times e to the k times t. Like this is the solution to this differential equation. Anything that's growing exponentially, you can model that way if it's continuous growth. Notice again that we said before, if the k value is positive, it's growth. If the k value is negative, it's decay, something declining. It's the rate constant. Okay, that rate value is a decimal. The second page here is a similar kind of problem. If you think about this, think about if you if a tire is punctured, the air is going to come out most quickly when? Yeah, right away when you first puncture it, and then as the pressure goes down inside, it's going to come out more slowly. All right, so it's going to be something that can be modeled with an exponential function because it's going to drop most quickly here, and then it's going to go slowly after. Eventually, I realize it goes down to where the pressure equalizes with the outside pressure or whatever, but in that case, it's kind of asymptotic somehow. So we're modeling it a little more simply than it is here, right? But that being said, we can still write a simple model function for this here. Differential equation that states this fact that it says the rate of change of air pressure inside the tire, which you can call conveniently enough again, P.
Wow.
So when you're copying your work from the previous page, you can just don't even have to change the letter.
That's cool how you did that.
It is directly proportional to that pressure, right? So the rate of change of pressure is whatever here, constant times the pressure itself. Now you might have to solve to find this. In the previous one, that k value was given. Here we know that you got to find the k value. Find k here.
Oh, I see.
I've given you some different information, right? This is the oh, to find it, there it is. No, well, you have to actually. This is the rate, right? 0.28 psi per minute.
0.28.
This is not like I haven't given you the k value like in the previous one. This says that the pressure was 35 psi here and is decreasing at that value, right? At time 0. At the beginning, the pressure is 35, and that's the rate. The rate's not going to be the same the whole time because it's not a linear function. But it's saying right at the start, it's going down at this certain rate, and this is what its value was. It's 35, and the rate that it's going down is 0.28. You need to use those two to solve for this, right? So you need to say 0.28 is k times whatever 35 times 35, right?
Yep.
So then k is whatever that works out to. What is it?
0.008.
208, yeah, makes sense. All right, so then your differential equation to start with is that. It should be, you're very right. And the way we can, I guess that this is decreasing at that, so this should be negative 0.28. Good, very good point.
You're welcome.
Thank you. So this is your differential equation that states that fact. Okay? It should be negative, yeah. If you go through the exact same steps in solving that, ... what are we going to get to here? Yeah, population is pressure equals
E to the
35, right? Because that's the initial pressure. Yes, absolutely. That's solving it with the initial condition. What? Time would be in whatever minutes this is up here, yeah.